All right. So a couple of guys asked questions, particularly about problem 3 on the homework. And so some of the examples we'll look at today will be similar to that one. So we'll have some good worked examples here by the time we're done today. All right. So let's kind of go through and talk about some of the stuff with respect to second order. So let's pick up with where we were. All right. So in general, you know, I like to start with just a little bit of grounding in reality here. So, you know, these things do happen in reality. You know, so we're talking specifically about, as I said, second order circuits with constant sources. All right. So constant sources, meaning that they don't change with time. A lot of this class is going to deal with stuff where the sources do change with time. And that's where we're going to start on Friday when we talk about real AC circuits, right? So specifically where we've got sources that fluctuate with time, okay? And in those cases, you know, we don't, in case you're thinking, oh, well, we're going to talk about third order, fourth order. We don't really talk about that stuff, okay? There's good reasons for that, which is that most things can be approximated as first order or second order, all right? But we're gonna worry as we get into non-constant sources, or what we call AC sources. Those typically we're a little bit more worried about steady state, all right? With a constant source, steady state's a pretty easy thing to understand, and we worry about the transient condition. So, you know, what I talk about is, you know, sort of a similar example, or an example where you see this sort of thing is this thing I called an inverter, where I might have a DC source over here. And the example I gave was a solar panel is a good DC source. And I connect that over to a grid. And that grid is AC, all right? And so you'll see, you know, essentially what we see is a sinusoidal voltage over here. And you can see in this guy, it has this thing it's calling a filter, and I can see an inductor and capacitor. And we get these sorts of behaviors where I can see a second order behavior, all right? And the switching action that happens in these circuits, right? Like I said before, we talk about switches like this, right? They close at t equal to 0. Well, in reality, the types of switches that we're typically talking about are things called transistors, which are really electronic versions of switches, okay? So we get circuit behaviors that look like this, all right? And we'll see some examples, some practical examples as we go through the semester, but it's important to remember these things do really happen in real life. All right, so we've gone through, and the homework is structured this way. Essentially, it's in 6 steps, all right? Whenever we get one of these problems, we basically go through these steps, which is to say we get the differential equation, we solve it for the transient piece, we get the steady state value, and then we got to do some stuff here in steps 4 and 5 for the initial condition, and then we put it all together in step 6, all right? So we're going to, like I said, we're going to go through some examples of that today, but before I even do that, I want to remember a couple of things. So I kept this really general, x of t. I said in general, there's 2 variables for x of t that we'll talk about, right? Which 2 variables would I consider for x of t? What am I?
The inductor. The inductor.
Inductor what?
Voltage.
The inductor voltage.
No, not the inductor voltage.
Inductor current.
Current. Oh, yeah.
Inductor current. And what's the other one?
Capacitor voltage.
Capacitor voltage. Why those 2?
Energy storage.
These are the energy storage variables, right? We store energy in the inductor current. We store energy in the capacitor voltage, right? We don't store energy in the inductor voltage. We don't store energy in the capacitor current, all right? In fact, with constant sources, inductor voltages are almost always going to end up being 0 in steady state, and capacitor current's almost always going to be 0 in steady state. So let me ask you that question just to see if you guys, so I say capacitor current is pretty much, in fact, in steady state, I know that's always going to be what?
0.
0, right? Because there can't possibly be any current going through a capacitor in steady state. It becomes an open circuit, okay? All right, so really we deal with these 2 variables. And in the homework, I think all the problems in the homework have a capacitor voltage. All right, and problem 3, I think, is one that's confusing to folks. My first example is going to be similar to that one. Okay. All right. So a couple of things. All right. So these slides here, which I'll post after class, really have a good summary of the way that I like to look at this, okay? So we try to get our differential equation in the form that's given here, which since it's a differential equation, right, this just goes back to our analysis of differential equations, which says that any differential equation has two pieces. So I say a steady state and a transient, all right? So you guys should remember from just your differential equations class. I guess you haven't gotten there in 2254 yet, but if I'm talking about differential equations, the solution to any differential equation always has two pieces, right? In differential equations, what did you call those two pieces?
Particular and homogeneous.
Particular and homogeneous, yeah. So this guy right here is also the particular solution, right? If you're trying to match up what we're doing here to, so we're looking at things kind of a more of a physics-based approach than a math-based approach. And so in this case, the particular is the steady state and the transient is the homogeneous, all right? All right, so this matches up with everything you did there, okay? Now, from the differential equation, we get to what we call the characteristic equation that's got the two roots, okay? So we can relate the terms here in the roots to those coefficients in the differential equation. Now, what did I say always has to be true about those coefficients in the differential equation?
A and B always have to be positive.
A and B better always be positive. If they're not, that tells me that my solution will get bigger and not go towards zero as time goes on. That's not ever possible because that means that the energy stored in the inductor or the energy stored in the capacitor will go to infinity. And that violates the basic laws of physics, all right? I make that point because you guys get the differential equation from looking at the circuit. So if you end up with negative signs on, let's say the coefficient A is negative and everything else there is positive, well, then you screwed up something in the circuit analysis, okay? So that's an important point to remember, okay? All right, so we said that there's basically, you know, there's really four cases, right? But the three cases that we typically talk about: underdamped, critically damped, overdamped. So we look at alpha and omega naught to figure out the difference. So I want to ask you guys, so underdamped looks like what in this case? You know, what would an underdamped response look like? How would you describe an underdamped response?
You're going to get oscillations with the peak decreasing until it approaches zero.
Yep. I'm going to get something like this where it decreases like that, okay? And if I had overdamped, if I go down to that guy, he's basically just looks like an exponential response, just like a first order response, okay? Those are our basic approaches. Now I want to make a note. I did change the notation a little bit with respect to my last set of notes, which is to say that for all of these guys here, because I have essentially what amounts to two components, two exponentials in my transient response, there's always two unknown coefficients in my solution, okay? And the book has basically, I think it's B1s, A1, B1, and D1 is what it calls. So it calls them, in one case it calls them D, in one case it calls them A, in one case it calls them B. In other words, these unknown coefficients here, it uses a different letter for each one. I find that to be just a little bit confusing. So I just left them all as the same, okay, in this case. All right, and we're gonna use that again here today. All right, so we talked about what these look like. All right, so let's look at any one of those cases, right? So if I had x of t equal to, I don't know, it's always got the final, let's say plus a1 e to the negative s1 t plus a2 e to the negative s2 t, okay? So let me ask you this. If I just wrote that out there like this, which one did I write out? Which solution type?
Overdamped.
Overdamped, okay, two exponentials. And I guess to stay consistent, I didn't say negative. I just said S1 and S2 like that, okay? Now, I get two unknowns. So to be able to solve for those two unknowns, I need initial conditions. What two initial conditions do I always need? One of them has to be x of 0, right? I need to be given the initial value of the variable. But what else do I need?
The derivative.
X prime of 0.
Yeah, the derivative at 0. Now, In particular, I'm going to say 0 plus, right? Always, because I need to figure it out usually right after the switch moves. Because right at t equal to 0, usually there's switches moving and it's hard to sort of define it. But because we care about t greater than 0, we look right at 0 plus to see what's happening. All right, again, we'll see some more examples today. So that means I got to take the derivative of this thing to be able to figure out a1 and a2. So if I take the derivative of that with respect to time, what happens to x infinity always?
Goes to 0 or 1?
Goes to 0, yeah, because I'm talking about constant sources. The steady state always has to be a constant value. So this guy is going to work out to s1 a1 e to the s1t plus s2 a2 e to the s2t. Now, at t equals 0, that guy simplifies nicely, doesn't he? What's he going to simplify to? What happens to e to the s times 0?
Goes to 1.
Goes to 1, right? So this guy's going to go s1 a1 plus s2 a2. Now, if I do that for something like this guy, well, that's kind of ugly, right? Because I have all kinds of time domain expressions there. So what I did was try to summarize those here for us, okay, and put these in the notes so you guys can look back to them. If I take the derivative of that underdamped expression, all right, I got to do chain rule, or not chain rule, it's the product rule, right? So the derivative of this guy times this guy, right? And then you got to reverse that. So I get the expression that's shown here, and I didn't want to waste time doing the calculus on that here. All right, if I plug in into this first expression right here, if I plug in t equal to 0, right? What happens to cosine of 0?
It should be
1.
Becomes 1.
Should be 1. What happens to sine of 0?
0.
Becomes 0.
0, yeah. And then I do the same thing down here, right, on this guy. Except so I know that this guy becomes 1, 0, 0, 1, and this thing simplifies to this, okay? So what I have is a system of equations with two unknowns, and my unknowns are a1 and a2. Now this one's kind of simple once I get it down to this, right? It's very easy for me to solve for a1 and then plug it in for a2. But in general, it may not be as simple, all right? So we're gonna look at how I approach that today. And you can do the same thing for the critically damped. Again, you guys can do the calculus, you know, to get this. I just didn't want to go through it here. Case 3, similar, I can do the calculus, but I get to those results, right? So if I take, you know, in combination, if I take all of my equations that I piled up from, I don't know, the beginning of this slide deck, basically from here all the way down through to here, all right? You should have everything you need to go back to be able to work through sort of the forms of the equations that you need. I tried to get the equations down to as simple a set as I could. Zybooks has 1 billion of them, I think, too many. I think this is a simpler set, all right? And you guys can argue with me, maybe it's not, but we'll see as we go through some examples today, okay? Now, the big thing is how do we enter these sorts of things into MATLAB? So I'm giving you this as well, all right? You guys are not, you know, totally proficient. I know you're not totally proficient in MATLAB, so that's why I tried to give you these expressions here. So in any of these problems, all right, what I typically do is, in fact, I will always give you the time vector, right? So in the problems, and we'll look at, so in recitation on Wednesday, we'll definitely look at some example problems that are created like this that we'll put into MATLAB, okay? But the solution that you enter will always have one of the 3 forms that is given right here, okay? Now, I may be asking you for a current, so in other words, an I instead of a V, but it'll have these forms, all right? Again, the tricky thing about this, and the reason why I'm giving this to you, all right, essentially is because of this particular piece here and here, all right? In MATLAB, if you think about it, cosine omega dt, if t is a set of numbers, that means that cosine omega dt is going to be a set of numbers. And MATLAB has trouble making those multiplications, okay? I don't want to go through the details of that. You can look up what this is called is a dot multiply. If you want to look that up in MATLAB. Yahoo hopefully will teach you about that in 2254. But you know, suffice it to say, you can go back to this slide to figure out what you need to be able to be able to enter your solutions into Canvas. Okay. All right. Again, we'll look at some examples of applying this here as we go through class today. All right. Any questions here? All right. Hopefully there'll be some questions later as we go through this. All right. So, all right. That's our overall solution process. All right. 6 steps. Homework set up to follow those 6 steps. Okay. And, you know, we got to go through and try to work that out. All right. So we're going to start out with an example problem. And I worked this one out in MATLAB. So I'm not putting it into Canvas per se, but I did enter this into MATLAB in the way that, that I would enter it. All right, so here's the problem. In this case, I'm given a series circuits. I've got RL and C in series, and there's a 48-volt source connected there. I'm told I'm closing that switch at t equal to 0. Now, somehow, some way, I know that IL 0 minus and VC 0 minus were 0.1 amps and 10 volts. There had to be something else going on in the circuit to make that happen that we don't see, but those are the values that we're told, okay? Now that's very similar to what you got in problem 3 on the homework, right? Problem 3, I give you those initial conditions, all right? And you guys can work from there, all right? So we want to go through our process here, all right? So in this case, what I'm being told is that x of t, so the variable I want to solve for in this case is I sub L, the inductor current. Okay. All right. So how do I start this? How would I start this problem?
Do a KVL equation to get your second order differential equation.
Do a KVL to get my second order differential equation. All right. So let's try that. All right. So I'm going to write this out symbolically. L, R, and C. All right, so I'm gonna do my KVL. So once the switch closes at t equal to 0, there's gonna be a short there. All right, now one thing I wanna be clear about too is I wanna define all of my directions at the beginning, and I'm gonna stick with it from there, okay? So I'm gonna say V sub R like that, all right? Now I'm going to write off to the side the things that I need to know here. So V sub L, how does V sub L relate to the current in this case, or any case? V sub L equals what?
It would be V sub R divided by R.
Nope.
L di over dt.
Yep, L dIL by dt. Okay. And then what's my other relationship for the capacitor here?
C dV dt.
C what?
C dV dt.
dP sub C over dt.
Yep. And that has to be equal to the inductor or the capacitor current. Okay. And all right. So so to write that differential equation out, or I'm going to start out, somebody said KVL. So I'm going to start my KVL here, and I'm going to work around in a clockwise way. So I go minus to plus on the voltage source. So I say minus 48. And then I see everything else as I've written it out as plus minus. So I'm going to say plus VL, plus VR, plus VC, like that. Okay. So now I'm going to rearrange it and say 48 has to be equal to V sub L plus V sub R plus V sub C. Now I want to have a differential equation for I sub L, which means that somehow, some way, I need to get an I sub L into each of those terms here with a second order derivative, a first order derivative, all that stuff. All right, so how should I do that? Help me out with the first two terms. What should I put in for V sub L?
Just substitute for L d DIL dt.
Yep. Okay, L DIL by dt. Okay, that's in terms of IL, so that's good. What about V sub R? How would I deal with that? What would I put?
Wouldn't it just be I sub L times R?
Yep, I sub L times R, right? Just Ohm's law in this case. Now, V sub C, here's where the problem comes in. How do I deal with V sub C?
Could do the integral of I sub L times 1 over C.
Okay, all right. So basically, whoever that was has the right idea, right? So what do I know about I sub L and I sub C in this circuit?
They're the same.
They're the same, all right? They have to be the same, all right? And I sub C equals C dVc by dt, okay? So looking at that real quick, that tells me if I rearrange this thing, what I see is that V sub C, just rearrange it, dVc equals IC dt, like that, over C, okay? So I just sort of rearrange my differential equation. If I integrate both sides of that expression, I get V sub C, right? I just undo the integral here. V sub C equals 1 over C I sub C dt, like that. Now, if you've looked at problem 3 on the homework, it's a similar situation. In that particular case, you have 3 currents adding up from a KCL. In this case, I've got 3 voltages adding up via KVL, right? But the approach is going to be similar if you try to tackle that problem, okay? All right, so, and we said I sub C and I sub L are the same. So I'm going to say 1 over C integral I sub L dt, okay? So 1 over C integral I sub L dt. Now, is that a differential equation per se? Certainly not. That's not the normal way we're used to looking at a differential equation, is it?
If we take the derivative of both sides, we can get it as a second order.
I can take the derivative of both sides, right? So if I take the derivative of 48, what is that? What's the derivative of a constant?
0.
0, right? So I have 0, okay? And what about, what if so when I take the second derivative of the first term right here, what does that become?
Squared I dt times L.
Yeah, it becomes the second order term. If I take this guy here, it becomes the first order term. Now what happens if I take the derivative of an integral like that?
It cancels out.
Cancels out.
Yeah, it cancels out. So that turns this whole thing into L d squared IL by dt squared plus 1 over R DIL by dt plus 1 over C times IL. And I've got a first order differential equation. Is that in my standard form though that I gave us?
No.
No. Yeah, my standard form is basically this guy here. So I want to get that second order term to have a coefficient of 1, right? So basically, what do I have to do to get a coefficient of 1 on that first term?
Divide everything by L.
Yeah, divide both sides by L, right? So I'm going to say I'm going to get to 0 equals d squared IL by dt squared plus everything through, what did I do? Okay, I see what I did wrong. That's an R right there. Yeah, I made a mistake when I copied over, right? It should have been IL times R in that middle term. So this becomes R over L DIL by dt plus 1 over LC. All right, IL. All right, now what I did here is the way that I would put this into MATLAB. All right, so what I do when I start entering my MATLAB is I put in the values of each of the components here. So I put in L equals 0.1, C equals 0.4 times 10 to the minus 6. So you put this in, this E minus 6, that's the same way that you would do that in a TI calculator, right? I think a TI calculator is capital E, right? It's little e in this for this guy, but it's the same scientific notation, all right? And then R is 280. So if you look at what I did here, right? So here's where I had the values. This was 100 millihenries, 280 ohms, and 0.4 microfarads. All right, so I entered those values like that. Now, when I go into Canvas, you know, when I play around with Canvas, I always add this stuff to the template that I give you guys. Now, when you come into Canvas, what you're going to see is A square brackets, B equals square brackets. Okay. Now, I saw Kamal put something into the Discord right before we came into class. We always put those square brackets there, and I do that on purpose because if we don't put something that's blank, like the square brackets that are blank like that, when you guys go to run your code, if you haven't done the whole problem, it'll generate errors automatically just from those variables. Okay, so we put that there. You can leave those square brackets or you can get rid of those square brackets. It doesn't matter. All right, it really doesn't matter one way or the other. All right, it's up to you. Okay, but I make that note because I saw that question kind of come up. So I can get rid of them if I wanted to. So in this case, I guess I got rid of them. But notice what I did was I just pattern matched here. And I said, well, A is R over L and B equals 1 over LC. Okay, that's how I would do this if I were just kind of entering stuff in MATLAB like this. I like it like this because then I can kind of easily see all the equations and I can check to make sure that my equations look right. It's a lot easier than just trying to look at each entry on my calculator. And if for instance, I entered, you know, let's say I put 4 microfarads by accident instead of 0.4, I can very easily rerun everything and see what happens. Okay. Any questions about what I've got here? Okay. All right. So that's what I've got here for step 1. All right. And if you guys have questions, ask the questions, turn on your microphone and ask the questions. It's really hard to keep track of the chat while we're going. If you guys want to ask.
Did you go back to the first slide where you were like actually implementing all the derivative stuff?
This guy?
No, the first one. It was all in red, not the actual formula. Like when we were doing this problem with the circuit. Yeah, there you go. So the 48 goes to 0 because you did a derivative there, right? Or are we just subbing?
Yeah, no, I took the derivative. And just to be clear, you know, let's say I could write it this way, d by dt and d by dt
Okay.
of all of that. All right, I should be careful of that because that's not exactly the way I've written it out here. Right. So the next, so it's because I took the derivative of both sides. The derivative of 48, right, is 0.
Mm-hmm.
Okay. All right. So real quick, from my differential equation analysis too, if you look at that, the particular solution to that has to be 0. All right, because it's equal to 0. So that's going to match up with the physics, of course, as we go through this problem, right? But that's step 1. Step 1 is basically just to go through this stuff. Step 2 is we say, all right, well, I want to solve the differential equation and find the general form of the solution. I don't have enough yet to solve it completely, but I can get the general form of the solution. So what do I need to do? What's the key step here that I need to do to figure out what the form of the solution is going to be? What do I have to calculate?
Do we need to find out if it's over damped or critically damped or whatever?
Yeah, I got to figure that out. So how do I check that? Given what I know here.
Find alpha and omega.
Find alpha and omega, right? So basically what I do is I go back to my, my forms here. So my solution types are the 3 ones that I've given here. So if it's underdamped, critically damped, or overdamped, right? So underdamped is where alpha is less than omega naught, and overdamped is where alpha is greater than omega naught. And what that's doing, right, is it's looking at the roots of that characteristic equation and trying to figure out, well, is the value under that radical, is that negative or positive? All right, that's basically what we're checking. All right, and what I did was I gave you the relationship here between alpha and omega naught, how they relate to the coefficients in that equation. All right, and so what I see is alpha is a over 2, omega naught is the square root of b. Now, first of all, a couple of things. You know, if you're comfortable with differential equations and all that, you could just look at the roots of the solution and figure this stuff out without knowing any formulas for alpha or omega naught. All right. You could just get the roots of this characteristic equation and you can figure out from what the roots look like, what the solution is. All right. And if you're comfortable with that, you know, do it that way. That's perfectly fine. All right. The key thing for me is I teach it kind of the way the book does here, which is to sort of what are these relationships between the coefficients here and the alpha and omega. So I'm given that relationship, and because we're always put in a standard form, alpha is always going to be the middle coefficient divided by 2 and the square root of this second coefficient here, okay? So in that case, I just go back, and this is pretty straightforward for me. Once I have A and B, what I do is I go into my MATLAB and I put in alpha is A over 2 and omega naught is the square root of B. Okay, I put those in there and I run that. Okay, so and what you would do, like in Canvas, you could click run script in Canvas, or you could click the submit button, right? You can do either one. If you click the submit button, it will count it as an attempt, but you have unlimited attempts, so it doesn't really matter. All right, and when I do that, I'm going to get my value. So here is alpha, and here is omega naught. So it looks like alpha is less than omega naught. Okay, so which one of these do I have? Alpha is less than omega naught. So which case do I have?
Underdamped.
Underdamped. All right, and the problem is, I'll go all the way back here so I can see it, right? Underdamped, alpha less than omega naught, right? Overdamped, alpha greater than omega naught. So the reason I look at it this way is when alpha is less than omega naught, I got a negative sign under that radical, and that's when I get the cosine stuff. So this is the case that I've got here, okay? This one, underdamped, right? At that point, I have it, okay? So what I see is that means my form of the solution is going to be this guy, okay? And I'm going to need to calculate this omega d term here. So omega d is omega naught squared minus alpha squared. That's the frequency of this sine and cosine, okay? So let's go, I'm going to write that down for ourselves here. So in this case, this guy is for me x of, well, not x, right? I'm solving for IL. So IL of t is whatever my final value is, which again, we haven't, that's step 3. We haven't figured that out yet, times e to the negative alpha t times a1 cosine omega dt plus a2 sine omega dt, okay? And then I also need to calculate this whole omega d guy. Omega d is going to be omega naught squared minus alpha squared square root, okay? I'm going to leave it in that form in MATLAB, and I'm going to keep alpha and omega naught and omega d as variables, okay? All right, so so right now it's nothing for me to calculate. That's the end of step 2. I know it's that, right? I know it's underdamped. And there is nothing else to calculate for step 2 because I don't know what this value is yet, and I don't know enough to get A1 and A2. So that's all I can do at this point. All right, so now I jump to step 3, okay, which is to find the steady state values IL infinity and VC of infinity. Now, technically, I don't need to know VC of infinity, right? Because I'm not solving for that, but I'm just, for good practice, I'm going to look for it anyway. All right, so let's do that. This is a pretty easy step in this case. So steady state values. So if I get to steady state, this is long after the switch is closed. All right, so long after the switch is closed and I've reached steady state, all the transients over, what do I know about an inductor?
It acts like an open circuit.
Short circuit.
Short.
I mean, the short circuit.
Short circuit.
Yeah, the inductor acts like a short circuit.
Right. And if you don't remember that, always remember VL equals LD IDT. So if the currents become constant, that voltage has to be 0. All right. So that inductor becomes a short. The resistor is there. What do I do with the capacitor?
Open circuit.
Open circuit. Now, checking the signs is always important here because, you know, I want to make sure that I draw this current having the same direction as the one I gave originally. The question?
Yeah, how are you doing, doctor?
Good. What's up?
I'm good. I'm good. I think.
I don't think he knows his mic is on.
Yeah, I don't think he does.
Yes. What was that?
Hey, if you're not talking, go ahead and mute yourself. All right. Hopefully.
Dr. Cox, I think you can mute him.
Yeah, if you go to the view options, I think you can mute everybody.
Yeah, which
is annoying to have to do, but
annoying to have to do. Yeah. Probably under participants. Yeah. All right. And all right, this will allow you guys to unmute yourselves. So just unmute yourselves as you need to. Yes. Doesn't.
All right. I think is it working?
I don't know. It doesn't seem to be.
I still hear it.
Doesn't seem to want to be listening to me. I'm clicking mute all current and new. All right. All right. Well, we'll see if that works. You guys can unmute yourselves as you need to. All right. So, if I look at what I got here pretty clearly, what is VC of infinity? What is this guy?
48.
48, right? And what's the current?
0.
0. Has to be 0, right? Because there's an open circuit there. So that's consistent. If I had just looked at this as a differential equation here, you would have said the particular solution was 0 as well because the whole equation is equal to 0. So it squares up with what you should know from differential equations. Okay. All right. So at this point, I've finished with step 3. All right. And so I would enter that into MATLAB, which we'll look at a more complete thing here in a second with the MATLAB example. But let's go to our step 4. Step 4 says analyze the circuit at t equals 0 minus. And this is a very trivial step, right? So I was told here in this particular case that V sub C of 0 minus was 10 volts. And I was told that IL of 0 minus is equal to 0.1 amps. Okay, I was told that back on the very first slide, right? So I was given these values. Now, this 4th step is pretty trivial because what is it saying? Well, it just says that the capacitor current has to be continuous. Inductor current has to be continuous. Capacitor voltage has to be continuous. All right. V sub C of 0 plus and I sub L of 0 plus. They're found and they're solved, right? The thing is, the inductor voltage and capacitor current, those do not have to be continuous, okay? These guys do. Because of conservation of energy, these guys have to be continuous. So that gives me one set of initial conditions, and it gets me over to step 5, which is I need to analyze that circuit at t equals 0 plus now and figure out what those derivatives are, right? Why am I doing this? Why do I have to find these things again? What's the point of this step? Somebody tell me.
In order to get to our equation in the general form?
Yeah, in order to solve for those unknown coefficients in that general form, I need a condition for the derivative. Since I'm only solving for IL in this case, I technically only need this guy. But again, for good practice, I want to figure out both of them. All right. So what did I say right after the switch closes? So basically what we're doing is we're saying at t equals 0 plus, that's right after the switch closes. So I got my 48 volts. I've got my inductor, I've got my resistor, I've got my capacitor. Okay. This is at t equals 0 plus. What did we say we do? What happens with an inductor? What do we say is true about the inductor current at 0 minus and 0 plus? What has to be true about that?
They're both equal.
They're the same.
They're the same. They're the same. And the same is true about the capacitor. So we said IL 0 minus equals IL 0 plus. VC 0 minus equals VC 0 plus. So how do I replace the inductor in this case? How can I model the inductor for this really short period of time here?
A current source.
Current source.
Current source. All right. Now I got to be careful with the direction of that current source, right? It has to be in the same direction as my IL, right? So I'm going to say he's got a direction like that. All right. And I was told that, so this guy here is, I need more space. IL, give myself some more space. IL 0 plus, which we saw on the previous slide was 0.1 amps. Okay. This here is V sub L, 0 plus. Okay. I wrote it plus to minus like that because that's the way I defined it all the way back at the beginning of the problem, right? I wrote V sub L plus to minus like that. All right, that's going to be important here in a second. All right, so I'm going to write that plus to minus like that. And then I have V sub R across this guy. Okay. And what do I do with the capacitor here?
Voltage source.
Voltage source. And its value is going to be V sub C of 0 plus, or 10 volts. So it's like that guy is acting like a voltage source. Okay. All right. So now what I want to get to is I want to figure out these derivatives. Okay. And I got to remember dVc dt equals what? What does dVc dt equal to?
IL over C.
Yeah, I'm going to say in general, IC. In this case, IC and IL are the same, right? But IC over C. And then if I looked at DIL by dt, what's that equal to?
VL over L.
VL over L, okay? So this says that what I want to do in this case is I want to look at that circuit and I want to solve for IC and I want to solve for VL and then use that to find the derivatives, okay? So let's redraw the circuit over here. So basically what I'm saying is I got 48 volts. I got a current source of IL 0 plus. This is VL. I got this resistor here with V sub R. And I have a capacitor over here, which we're saying is V sub C of 0 plus, or 10 volts. Okay. All right. So what I need to do is I need to solve for V sub L of 0 plus. That will get me to DIL by dt of 0 plus. And I need to do the same thing for I sub C of 0 plus. That will get me to dVc by dt of 0 plus. Okay, so let's do the easy one here first. What does I sub C of 0 plus have to be? If I look at this circuit, I sub C, the capacitor current at 0 plus, what's that got to be in this case? If I'm looking at this circuit, what's the capacitor current?
Is it 0?
Nope.
IL.
IL, right? Because I got a current source that's basically pinned. The way I think about this is the current source forces the current in that circuit to be whatever it is, IL of 0 plus, which is 0.1 amps, was what we found on the previous slides. So 0.1 amps. All right. What about the inductor voltage?
Vs minus Vc.
Not quite.
If it's when the switch opens.
I got it. So I'm looking at the circuit. I'm looking at the
VR.
circuit. I'm looking at the circuit that I have right there, right? So if I give you a circuit and I say I don't know VL, I got to do what in that circuit?
KVL.
KVL, right? So I'm going to do 0 equals, and again, my KVL I usually do going clockwise. I'm going to say 0 minus 48 plus VL of 0 plus. That's the voltage across this current source. Plus V sub R plus V sub C of 0 plus, like that. All right. So if I rearrange this guy, I'm going to see that VL of 0 plus equals 48 volts minus V sub R minus V sub C of 0 plus. What is the V sub R here? What would that be?
R times I sub C or I sub L.
Yeah, R, yeah, minus R times I sub L of 0 plus, like that. Minus V sub C of 0 plus. And if I want to put numbers in there, I'll say that's 48 minus R, whatever that is. I forget what that is off the top of my head, but it doesn't really matter. So R times 0.1 minus V sub C is 10. Okay, now, here's how I do that. Okay, so what I do typically here in MATLAB is I set this all up in terms of the equations, right? That way I know I'm minimizing my math mistakes. All right, and some of you guys have started to tell me you've started to do this and you start to see the benefit of being able to maybe better track your math here, okay? So what I see here is I put in all my component values, 0.1 for the L, 0.1 or 0.4 microfarads for the C, 280 ohms for that guy. And I put in my initial capacitor voltage and my initial inductor current. And I have this guy V equals 48. That's my 48 volt source. So what I do here is, you see I've got my equation VL 0 plus. This equation right here is the same equation I have here. All right, and you can take a quick look at that later to see that that's the same. And I see 0 plus is the same as the inductor current. That's this guy right here, okay? And what I have to do is what I'm saying is, so I know that V sub L equals 1 over L DIL by dt. What am I saying? Right. I'm saying that, yeah, V sub L over L is DIL by dt. Sorry. And I sub C divided by C equals dVC by dt. So what I did here was to basically write down that equation for myself, and I solved for those guys. Okay. Now, when I run that, what I see is, these results here, right? So I see that the initial inductor voltage is 10 volts, right? That's what I had here. If you run this through, you're going to see that this guy is 10 volts, okay? And the initial capacitor current is 0.1 amps. So this tells me here, this guy here is DIL dt at 0 plus. And this guy here is dVC dt of 0 plus. All right. Questions about that?
How did you get the capacitor voltage at 0 plus to be 10?
Because I was told that at 0 minus it was 10. And 0 minus and 0 plus have to be the same.
Oh, wait, so that was an initial condition?
Yeah, that's in the initial conditions. Problem 3 is like that too on the homework. If you look at that, you'll see at the top of the problem, it tells you what the value is at T0 minus. I think people didn't see that in the problem statement. Okay. All right, questions about that?
I have another question. How is it that for 0 plus the inductor and the capacitor can be changed to a current and a voltage source respectively?
Well, what it's so if you go back and you look at the lecture from last time, right? What we say is that over a short enough period of time, right? This is the idea. Over a short enough period of time, the capacitor voltage is the same, right? And over a short enough period of time, the inductor current is the same. So let's say I was looking like 1 nanosecond before the switch moves and 1 nanosecond after the switch moves. For that really short period of time, the inductor current's constant and the capacitor voltage is constant. So I can replace them with sources. That's not true in general, right? I mean, I can't do that forever, but for like a couple of nanoseconds or something, that makes sense, right? And that that's true because of the fact that the energy, because those are energy storage variables, energy has to stay continuous. So the capacitor voltage stays continuous. The inductor current stays continuous. Okay.
Thank you.
Yep. All right. Now, that's not a true statement for very long. It may even be less than a nanosecond. Depending on the values, it may be a picosecond, right? But it's still true for some short enough period of time that we can make that decision, all right? So now we got to use those initial conditions now to find the unknowns in my solution. So the one that I need here is this guy, which says that the rate of change of the current is apparently, that's the units on that guy would be 100 amps per second at t equal to 0 is what that's saying, okay? You look at the rate of change of the capacitor voltage, it's enormous. It's 2.5 times 10 to the 5th volts per second. But that's a rate of change, right? It's not to say that that's a rate of change that's very high. That's feasible, okay? All right, so what do I do when I get to the 6th step? What do I got to do? What's my job here? Well,
writing the general form?
Yeah, put the general form down and figure out what all the values are, right? So what I do is I go back then to that sort of compilation set of slides that I got, right? Where I said, okay, well, in the underdamped, critically damped, and the overdamped cases, I got all these formulas. We said this guy was underdamped. So what I'm going to do is I'm going to take these results here for the initial conditions. I'm going to plug them in here, right? So I'm going to say, if I jump ahead, all right, so I'm going to go to here, right? X of 0 equals X of infinity plus A1. So this is what happens when I simplify these guys and put in t equal to 0. So in this case, I have IL of 0 is equal to IL of infinity plus A1, right? And DIL by dt of 0, and again, technically 0 plus, right, equals negative alpha A1 plus omega D times A2, okay, like that. Now, what I do is I have numbers for this guy. So this guy we said was 0, right? And this guy we said was 0.1 amps. So right off the bat, what is the value of A1?
A1 is 0.1 amps.
It's 0.1 amps, okay? So technically I just plug that into here, right, and solve, all right? And that's perfectly fine to do. I'm not gonna do that just because I wanna show how to set up a set of equations, all right? So if I look at it this way, I'm gonna say I have IL of 0, I'm just gonna consider it a variable, equals IL of infinity plus A1. So I'm going to rearrange that guy to be IL of 0 minus IL of infinity. So in this case, right, we know that that's 0.1 amps. So let me just write it that way. 0.1 amps is equal to A1. And I'm going to say plus 0 times A2. I know that I don't need to, but I'm going to write it that way. Now the other equation, DIL by dt of 0 plus, that guy was equal to 100. And that was equal to negative alpha A1 plus omega D times A2. Now, alpha and omega D are just numbers, but I'm looking at this. I got two equations and two unknowns, okay? Right, so the way I'm going to set that up is I'm going to say 0.1, 100 equals A1, A2 like that, okay? Now, what numbers do I put into the matrix there? What do I put in the top row?
1 and 0.
1 and 0. What do I put in the second row?
-1 and then...
No, not -1, negative alpha.
Oh.
Right, because it's the coefficient on the A1. So negative alpha times A1 plus omega D. Omega.
And those are just numbers, correct?
And those are just going to be numbers, yeah. So that's
because in MATLAB we can system solve with variables, right?
You can, totally. So here's how I set that up, right? So what I do is I have omega D equals that. All right. And you can follow through what I did here, but essentially what I did was I set this guy up as y equals c times a, okay? Where y is the thing that I just wrote. So this is my y. I guess I'll do it here. Y equals c times a. So this is c, this is y. This is a. Okay. And if you look at what I did, so here's the C, I wrote 1, 0. Now the important thing, I talked about this there's an example video that I posted on the Canvas page, right? When I'm entering different rows, I put a semicolon in between those rows, okay? That's what I do here. Again, you're not obligated to do that. You could do this any way you want, right? But I like doing it this way because that allows me to easily put everything down in front of me and I can just track my variables really nicely. And then I get those values right there. So so this guy here is A1 and this guy here is A2. Okay. Questions about that? All right. Again, no obligation to do it that way, but I find it again to be a lot easier to set up a system like that. Now,
Could you go back and tell how you set up the matrix for that you're actually solving? Like the slide before this.
Yeah.
Okay.
So basically, the first equation here, 0.1 equals A1 plus 0 times A2. So what I'm doing here is I say this entry times this entry plus this entry times this entry. That's the first equation.
I haven't seen that. I've always used augmented matrices, so I haven't seen that form in a while, but that makes sense.
Yeah. Well, even if you use augmented matrices, you should have seen this form at some point, right? This is the way you always sort of set up stuff, and the augmented matrix kind of comes from this, right? But hopefully that should make some sense. I mean, as long as you understand how that multiplies that.
Yeah, it makes perfect sense. Thanks.
And you could use the augmented matrix if you want to solve, right? This is just showing you the sort of a simple way to do it, where I do the inverse of this guy times those values. Okay. All right. So what do I do? Then I go back to what I do is I will always give you the time vector. There's no reason why you would know the time vector, right? I will always give you that time vector. And I have a slide here where I basically say, all right, here's the forms: underdamped, critically damped, overdamped. All right, you can go back to one of those formulas and just enter that guy in there. That's what I did, okay? And I did that, and here it is. There it is, okay? All right, so I put A of 1. So this guy here is the first entry here. So the 0.1, and A of 2 is the second entry, okay? All right, and then I did a plot. And I like to do the plot because it helps me to make sure that things make sense, okay? So when I look at this, right, I see the underdamped behavior, all right? So in other words, I see a decaying sine wave. And I say it lets me do a check because I know a couple of things, right? I know that IL of 0, we said was 0.1. And I know that IL of infinity was equal to 0. So IL of infinity, that's clearly happening, right? That guy's going to 0. All right, that's good. And then I can check this as well. Now, it looks like he goes a little bit above 0.1, but that's right because so if I zoom in, I see that it's actually a 0.1 at t equal to 0. But why does it go up before it goes down? How do I know it's going to go up before it goes down? How can I do a check on that? What do we know that can give us a check on that? Any ideas? Why do I know I'm going to go above 0.1 before I go down below it?
The initial conditions.
Because of the case it is?
The initial conditions. Okay, so what was it about the initial conditions that made you know that it was going to go up?
It's because this switch is being closed and there's going to be like an inrush of current when this switch
No, not necessarily. So when I look at this, so you're right, there could be some kind of a quote unquote inrush of current, but I solved for the derivative and I found that the derivative was positive. So DIL by dt was positive. So if I have a positive derivative, what's that mean about the function itself?
It's increasing.
It's increasing, right? That means I have to go up a little bit. Now, eventually I kind of come back down again. All right. So in other words, I can do some quick checks, right? So this guy has to be increasing at t equal to 0 because of the fact that the derivative was positive. If the derivative had been negative, he would have started out going down, right? So when I look at this, I like it. I like looking at that because I can justify from that picture that, okay, yeah, I'm seeing the things that I would expect to see, right? So that helps me to know that, you know, I've kind of got the right answer. All right. All right. Questions?
Oh, what's the difference between I've seen you like using WD in the formula and W0, like omega D and omega 0? What's the difference between them?
They're two different values, right? So, you know, essentially this form of the solution that I have right here comes from how you solve the differential equation, right? We call omega D the damped frequency. We call omega 0 the resonant or natural frequency. That comes from how you solve the differential equation, right? So if you went back, you'll see that in 2254, and you'd see that in differential equations, right? In this particular case, you know, in circuits, we just kind of give you the results of that analysis, right? So omega D is what we call the frequency of these cosine and sine. And that omega D value is always going to be less than omega naught. All right. But other than to say that's, you know, part of the form of the solution, I'm not going to say a whole lot more about that. That's kind of just the result that comes from differential equations.
Okay, so they basically represent two different values, right?
They do. They do. They represent two different values. And omega D has no meaning if I'm overdamped or critically damped. It only matters in the underdamped case.
Okay. Thanks.
All right. All right. So that was just the one example. I've got another one here. All right. And I've got my complete code all as one set here in this particular slide. All right. So you can take a look at how I entered everything. All right. And that's exactly, if you were to look at the solution to your homeworks, the solutions look like that. You know, and you know, where I've got all those other variables sort of defined, even though I've only given you in the template the ones that we're checking for, right? We give you those particular cases. All right. So yeah, I've got another example here, but we're gonna look at this guy on Wednesday. We'll look at this at the beginning of class on Wednesday, and so Wednesday's all examples. We're not going to go over any new stuff, just straight up examples. It's recitation time. We'll probably do 2, maybe 3 examples depending on time. Okay. All right. So I'm going to stop the recording.